Thank you, Kevin. Um, Good afternoon or good morning, depending on which part of the country you're in. Welcome to the research review session. And University of Akron is a member of the CCAT. And for the past 5 to 6 years, we've done several projects. So today is an opportunity to do the review for everyone. And because we have a lot of material to cover, I will be able to go through the topic and also objective of each project, and also some research and some work, but not too much in detail, and then the results. So here you see is the first project, and this project is to try to improve the operational efficiency. We try to study any advantages if we do some analytical or simulation work, and if it turns out to be positive, then is there a feasibility that we can implement in the field? So that's what we did in the first project. So here's a situation. Most of the intersections where a major road is intersected by a side road, and many cases we use a stop sign or actually the signal to control the traffic. Now, the signals works most cases first come first serve basis. In other words, it doesn't matter how much traffic is on the main line. As long as we have a vehicle waiting on a side road, side street there, long enough, the system is going to cut off the mainline traffic. So many times we see there are only either one or two vehicles waiting, and then the signal will have to switch to allow those one or two vehicles to enter. That will stop everybody. So obviously, this is not a efficient way to operate. And next, I have a few cases to show the situation. Okay. Now, first one is we have a vehicle want to make a left turn or make a right turn. In this case, a left turn, where we have vehicles coming from the going westbound. And even in this case, we're thinking if we have an autonomous vehicle following an ordinary vehicle, OV means ordinary vehicle, and then can we, the AV here, you see my mouse cursor, I'm not sure if you can see it, can try to adjust its speed, okay, so that we will separate the gap from the current T1. You can see here, it's between the two vehicles. And then extend that T1, so that's long enough for the vehicles wait on the side road to enter, okay, without the need to flip the signals. So that is the idea. Okay. In this case, we would have there's some technical equations we need to derive and the probability distributions, everything, but I don't have time to go through those. But anyway, in general, the T1 with some requirements, okay, would have to meet the requirements, the equations showing on the lower left-hand side corner. And the probability of success in this case will still be just the probability of such T1, how many such T1s exist there. And the number of vehicles that we can help through the AV to enter from the side road also, follow this equation, but we'll have a chance to discuss the equations more later. Now, case 2 involves a situation where I have 3 vehicles, okay? And notice the AV is in the, or called autonomous vehicles, is in the middle, and it is followed by another ordinary vehicles. Now, this case is a little more complex because the AV cannot just, reduce its speeds at the free will, okay? It has to consider the vehicles that are in the back there, make sure that, we do not create any blockage or even an accident, safety hazards for the following vehicle. Therefore, we have a issue of a T1 and a T2 here that will have to meet the requirements. And T1, T2, you can see we have an and sign here. That means both requirements will have to be satisfied. Now, in the equation here, the delta T is the time that possibly can be created by adjusting the speed of the AV, and the beta is the magnitude of adjustment. Okay, it could be like 10%, 20%, 30%, but we will discuss how to determine those beta next few slides. But in this case, pay attention to the probabilities. In this case, we will have two conditions. One is the T1 distribution, and also next is the T2 distribution. In other words, okay, this is the conditional probability. If T1 meets the criteria, T2 may not. Therefore, you can see we have a conditional probability. And of course, the number of vehicles can be created also follow a certain constraints, as you can see that. Now, next case is a situation where we have traffic coming from both directions. Now, if the vehicles on a side road just need to turn right, it has nothing to do with the vehicles on westbound. Only the eastbound vehicles, okay, will be considered. But we already discussed this situation. Okay, in this case, for right turn, the same for the eastbound or for the case 1 situation. But now, since we have left turn also, so we need to consider both directions. And then the equations, okay, we discussed it for right turns, but for left turns, if you look at the lower right-hand side equations, you can see with our T1 and the T2, in other words, the existing time headway between the two vehicles will have to meet these equations, okay? And of course, the probabilities here is conditional because for left turns, not only we have to look at the left, but also we have to look at the right. So it's a little more complex. Then the probability, of course, will be reduced. All right. Now, case 4 is the most complex, where we have vehicles in the front and also at the back of the in front and also at the back of the autonomous vehicles. Okay. And also the traffic coming from both directions. In this case, the criteria we discussed will apply in both situations. Now, for right turns, again, those equations we discussed, and now it's just more complex because we have to consider the vehicles that's behind the autonomous vehicles, and we discussed that situation. That is similar to case 2 for left turn. Now, for this case, for the left turn, situation is much more complex, as you can see. All those equations, I'm not going to go over to the details, rather just to show you the criteria, similar criteria. However, we will have to consider a joint possibilities. Therefore, you can see the probability you can see there is really conditional probabilities. And of course, number of vehicles that can be created will have to follow this equation. Now, again, we do not have time to discuss all those detailed equations. If you're interested in, you can discuss with me. You can follow up with me after the presentation. All right. So next what we did is to do the simulation, of course, to see if we propose all those models, whether there's any benefits by doing the simulation. Okay, and and after that, if the answer is positive, then we can do the lab testing to see whether technically this is feasible to do. And if yet the lab testing comes positive, then we'll move to the field to see whether any potential for field implementation. So that's what we did. Now, on the simulation part, there's a lot of data and everything. We do not have to review. I just need to report that simulation come out positive, and that means there's some good benefit. We can take advantage of this idea we discussed. So then we move to the lab testing. Excuse me. And we're trying to see whether technically this is possible. So what we do is try to use the equipment in a situation like here. when the vehicle from a minor street, come to the intersection approach, then our system can use the controller function to either delay the detection report or to extend the current time. I mean, that's for the green time for the main line, so that we can create some, time opportunities to use the autonomous vehicles in a traffic stream to execute the algorithm. Okay, so and we explored that. We tested the feasibility in the city of Akron traffic engineering, and the results show that it's feasible. We can do that, and so we're very happy. And then we move to the next stage, and that is the field test to see if any situation we should consider for possible field implementation. So this is one case you can see. The main line was stopped traffic. You can see that due to just like one or two vehicles crossing. You can see the minor streets, and that's a situation. If you can avoid, then we can reduce delay on the main line, and of course, and they reduce the interruptions of the traffic flow. Now, in the field test, this is the setup. Since we do not have autonomous vehicles, so everything has to be simulated. So what we do is, when a vehicle is pulling up to the intersection approach at a minor road here, you can see, then we we have observer, staying nearby, will report even before the vehicles pull up from a minor road pull up to the intersection approach. Our observer informs our vehicles, those AVs, or you can see CAV or AV, is our own. Okay, we drove those vehicles, and we have a place to wait for the situation. So when we hear that a vehicle is coming up to the minor road approach, our vehicle will come up following any vehicle in front, and then when we reach the speed reduction section, you can see that it's near the intersection, and then we'll start to reduce the speed to create, according to the calculation from the equations we presented, create a long enough gap for this vehicle on a side road to accept, so that the side vehicle can go. This is for left turn or for right turn. But for left turn, we did the same thing. But this is just an idea, simple idea, how we did all those. Okay. And here is the actual picture of intersection. We did a study. We did 2 locations. And if you can see the video, there's no sound in this case. And then we have a vehicle come in or slow down to allow this white vehicle to move. See, then you see the vehicle on the back there. If you see, that's our vehicle. We intentionally slow down to create enough so this vehicle will join. All right. Now the test results, we did the 3 situations again with the beta. Beta is the reduction in the speed, approaching speed for the AV. We did the maximum, we did the minimum, we did also an average. Okay. Now the beta, when you decide how much speed we can reduce for the the autonomous vehicles, we were not just doing that at random. What we did is we collected a lot of speed sample, and we did a little profile, speed profile, to find the percentage. Okay, so we dropped as low as 80%. Okay, 80%, and 85 percentile speed. Use that as a base, so you can see that we have a minimum 10%, a maximum is like 33 is like a 1/3. Okay, and that is a little extreme. We don't use that when we have vehicles behind, but there's again the criteria we discuss in the equations, and that is when we do not have any vehicles following the autonomous vehicles. Then we can do a little more aggressive, like 34% reduction. And the third case here is the average. Okay, so we did all different situations. Here are just like some parameters. So we that we used. Now, we did again 2 locations. One is in Akron, one is Stowe, and the city of Stowe. Both are in Ohio, in the greater Cleveland area. We have 43 cases for rights, and then for left turns, 23 cases. For Akron total, we have 66 cases. For Stowe, 55 cases. So in terms of the how many such gaps we created was accepted, you can see that the rate is 42 out of 66, and 30 in Akron, and 34 out of 55 in Stowe. The 2 percentages are shown in the 2 charts in the lower part of the screen. You can see that. Now, pay attention to this. 60% accepted the additional gap we created. 30% did not accept. So we found possibly a reason, people may not understand this. This is a new concept, okay? And maybe through education, from other, maybe for running for a while, a long time, people get more used to percentage-wise, it could be increased. But anyway, in terms of the objective, we think we have achieved the objective. Simulation showed, benefits, and the lab test showed feasible and technically feasible, and the field test we show that we do create opportunity for people to follow. In other words, if you do 64, or 62%, gaps that accepted by the side road vehicles, that sort of, it can be, indirectly can consider as reduce the traffic signal interruptions by 60-some%. So that is a good achievement. So we think this is a good project. Anyway, so let's move to the second project we did. This project is to analyze the possible impact of a roadway surface and a vehicle condition and other conditions on the autonomous vehicles fleet. Okay. Now the objective is to investigate again, roadway vehicle and a braking system, tire pressure, and other environmental factors on the formation of the autonomous vehicles. Okay. And then we for a long time, we were under the impression that when you have a autonomous vehicle fleet, more or less from many of the existing reports, the other literature, we see that more or less the vehicles look pretty similar. Okay, like in this case and this case, showing here. But in reality, we think in the future, the autonomous vehicle fleet, first of all, the fleet operation, there's literature shows there's advantages if we do the fleet operation rather than individual vehicles, because for a foreseeable, long year in the future, we will have to deal with a mixed traffic. That means autonomous vehicles mixed with ordinary vehicles. So it's advantageous to do a fleet. Anyway, so come back. Now, most cases, we will envision in the future, the autonomous vehicles fleet will be OD based. In other words, the formation or the fleet will be, formed in an ad hoc manner. Okay, vehicles going to the same destination with the same route probably will be formed in a fleet. So if that's the case, then we will have different vehicle models and also vehicle conditions, like tire conditions, tire pressure, braking system, power, all those things. Now, how do we determine, how do they follow each other? That is a question that we're trying to look into. If, you consider the pavement, the weather, and the vehicle conditions. So 2 focuses. One is to understand the impact of those all the factors we discussed, specifically pavement and also the vehicle tire condition, everything. So the issue 2 is we have to build a model, okay, that is able to handle all those different disturbances, the factors. Now, first of all, we did some pavements, study to find out, the effect of that. And we'll just go quickly on this. You can see, so through the experiment, we found, the friction coefficient is affected by a lot of things, including the weather and the rain and so on. And And also the braking distance is related, of course, to the not only the pavement surface condition, the friction coefficient, but also the internal tire pressure. And we're just going through this. You can see that lots of factors and affecting the braking effects. Okay. So from doing this, the above, we developed the understanding that if we use a predetermined parameters to handle the autonomous vehicles, the fleet, and it will not be enough really because of the conditions change. So we'll have to do a time dependent, okay, model. Excuse me. So first we start from building the basic equation. You can see Newton's law is used here. This is the main equation. The second equation is the engine and the power, okay, the force equation. If you're familiar mechanical engineering, you know the equations. So starting from here, and in the whole powertrain, we have a simple chart to show that out of the 100% of tank, we have like a 3% or 4%, 3% for air drag, aerodynamic drag, and also rolling resistance 4%. Now the numbers in parentheses means on highways, and the numbers not in parentheses means in the cities. But then if you pay attention to the most of the cases, and the vehicle road load is needed to cover the aerodynamic drag, the road resistance, and also the grade, okay, the slope. So, and then the vehicle fleet, okay, it's a platoon. Well, we all understand what platoon means. So basically, we're trying to follow the leader, and the platoon will each have a certain distance to follow. Ideally, everybody follow with the same gap or same distance, which is LD. But in reality, there's always some errors, plus and minus there, as you can see. The error EI here, and then in terms of the control policy, okay, we have, first of all, it's called constant spacing policy. Constant spacing policy says that if we want to maintain the error zero, in other words, then we want to absolutely maintain the spacing between any two vehicles as a constant distance. Now, this one we know is not the best way to do it, simply because it can be very costly and not efficient either. Because we all know when you go travel, if your speed is low, you really do not need to have a large space there. But when the speed is high, you need to have a larger space. So either you are doing a waste of spacing if you keep the LD to be very far, or if you make it small, then it will be unsafe when you come to like a 60 mile per hour, 70 mile per hour speed range. So the next type of control policy or law is what we call time headway policies. And that says if we introduce some speed related errors to the error term, as you can see, we added the error term in the right text, then this one will change according to the based on its speed. Now, so we continue on this. We don't have time to do much discussion on the detailed equations, but we use this control law, the time control, okay, headway control law there. And then we work on the equation, the basic equations, and then we come up with these control law equations. And this is the basic equation that we use to develop the functions. Now, in this equation, the K or kappa I is the engine input that you can directly understand that as how much gas you give, okay? And then we have the C, is 3 C's. They are the parameters, okay, that needs to be calibrated. Now, if you start writing it to draw the block diagram on in any vehicle, ICE vehicle, the block diagram will look like this. Now, again, if you're in the electrical engineering, mechanical engineering, you have to follow the diagram, the block diagram. This is for any vehicle, fifth, for eighth, you can see that, just an example. And now, that basic equation we will have to, in order to use to model the process, we have to convert it by using Laplace transformation, so that we are in a different domain. Excuse me, and then we obtain this transfer function. Okay, that's the main function that we're going to use to do this, simulation. Now, one condition for stability, it's simply can be understood as to maintain a system from going out of control. Any disturbance to the fleet somehow will be, suppressed and coming down, rather than and amplified and finally, become out of control. So this is the equation we'll have to maintain in order to maintain the string stability. Now, in order to achieve that, and this is the criteria, okay, that's the stability control become. So all the relationship between these parameters, among these parameters, will have to meet this criteria. And we did a lot of work to calibrate the parameters. All right, so this is the explanation, simple explanation of the stability. You can see that, okay, we have a rise time. Also, you can see that we have the time to peak and also, the final, setting time. Now, hopefully, the better system is the entire time from start to rise till the whole wave or disturbance or the oscillation start to settle. Then, if this time is shorter, then the model could be better. So that's another parameter. We do not want to have this oscillation, last, very long or forever, and that would be the worst case, or even, explode. Now, here are some results. You can see this is we use some parameters. You can see on the first line of data. You can see we have a fleet of 10 vehicles. This is in a simulation, and these 9 lines showing the spacing, okay, the inter-vehicle spacing between each of the 2 vehicles. You can see that they pretty much follow each other very well. Okay, and we change the situation. We change the initial spacing. Initially, when the vehicles start with 2 or 1 meter separate, and then we change it to 2 meters separating them. And but we have a desired spacing at, I say that at 2, so you can see that, they will come to the final, the 2 meter here, the vehicle spacing that we set after some, fluctuations or oscillations. Now, this is a situation where we do not set a common speed for them, but it's just letting themselves to adjust. You can see we have this kind of change, but the one on the lower part is if we set a shear speed for everyone to know that. So there's a target. So that will help them reduce the oscillation, the magnitude. At least they can see that here comes the 14, and here come to the 1.4. Yeah, 14. That's 114, not 1.4. And here is 10. So you can see the advantage of if we use a shared speed there. Now, those are all built into the equations. So this just shows some simulation results. Now, next, I want to say that because remember the objective of our study is to try to make the to consider the impact of the other factors like a pavement, the tire pressure, and weather and everything. So we will have to consider specifically the vehicle condition. So we'll have to redo the equations by adding a lot of other things in there. For example, the wheel load, okay, this will be the normal force here, and the distance from the center of the gravity center of the vehicle. Well, also, we have the frictions from each tire and other geometric parameters we'll have to consider. So specifically, after very detailed analysis, we come up with this equation. This is the full dynamic model. That will consider the driving and torque from the front wheel and the rear wheel, and also the braking, if the braking is taking effect from the front wheel and the back wheel. Excuse me. And we consider the aerodynamic force and all those like rolling resistance and also the grid resistance, everything. So this is the comprehensive model that will be able to take into consideration of the specific vehicle situation, the vehicle's weight, the vehicle's dimension, everything will be incorporated into this equation during the simulation. And a block diagram is much more complex. You can see that a number of places we can enter the data differently. So once you have the model, for example, if the roll resistance changed, you come to a part where it's bad, it's a worn up, the surface is worn, then the friction coefficient is low, then that will you go to the rolling resistance here. Okay, and that will change some parameters there. Or you have a ice roads or wet pavements, and then we can come to here. And you have other locations, so other parameters can be put in here. So we will just show you that this is possible to incorporate all different factors and to explore the impact. Here's some situation in terms of results. This is for real-wheel driving vehicles. You can see that, and any fluctuations quickly settle down. If a little disturbance, settle down, little disturbance, and settle down. So this is very quickly you can handle that. And this is a situation where it go uphill and this go downhill. You can see that there's some variations, but very small variations. And this is when we have a situation where, let's see, for vehicle 3, sudden, there's a braking on vehicle 3. So, imagine in the fleet, the vehicle 3 will start to brake, then the spacing between vehicle 2 and vehicle 3 will increase. You can see that increase. And then gradually it can coming back because the system is able to. So for this kind of disturbance, it converged again. In other words, the oscillation is suppressed, quickly to come to, the fleet. The reason, vehicle 3 might take a quicker break is possibly is there a pothole. We're just envisioning the situation. If there's a pothole, okay, the vehicle 3 detected that and suddenly take a quick break, and so that caused a little disturbance. But you can see that system is able to come back. So we have a lot of other situations considered. But anyway, just want to show this picture again. With this model, a lot of we have different places to incorporate the changes in the different factors. So that is the second project. And the next project we did is to develop a prototype safety advisory system to aid older drivers in gap selection. Now, this is a national data. Okay, this applies to older driver fatalities and all crashes. But specifically, let's move to the right side to see that. A lot of fatalities, happen at the unsignalized intersections. You can see that. The blue or gray is the urban area, the red is the rural area, but you can see that doesn't matter, urban area, rural area, the unsignalized intersections is way more than the signalized intersections for drivers. So then the question is how we may be able to help. And then this is the situation. You're familiar with the setting because in the first project we discussed, this is a gap selection. So whenever you come to a unsignalized intersection here, you can see doesn't matter you want to make a right turn or left turn. It's a lot of decision-making process there. And in fact, we all know, we all drive, right? When traffic is heavy, really it's hard for even for us, okay, for young people even to make a good decision and not affecting the mainline traffic much. So this is very challenging. So most cases, okay, people coming here, either to accept a gap or to reject the gap and waiting for another one. But during the process, they make mistakes. Okay, and that's why accidents happen, especially for older people, because the driving will require abilities in those all 5 above areas. And many studies have shown that when the older people, continue to age, then all those abilities start to reduce. And it's, not can it be used. I mean, the reason to explain why for the older people, okay, they have much higher than accident rates. Now, our research objective is to develop a safety warning system for older drivers 65 or above, and we will discuss how we try to fix the driver's age in this category, so that the system provide information for the older drivers to avoid unsafe gaps. Okay, we will discuss the design philosophy. Okay, when we discuss the technical part. The technology we use is V2I, and plus, of course, connect the vehicles in a system. But there are two situations. We have a controlled situation and an uncontrolled situation. The controlled situation is all the vehicles on the main road there, they have the V2I, okay, with a central terminal, and that is located at the intersection. On the uncontrolled situation, means on the traffic on the main line, nobody has this kind of capability. The system will have to measure it. In other words, we'll have to install traffic sensors to measure the approaching speed of the vehicles from either left or right or both sides, so that the system will know the speed, the approaching speed, and also the location and of the vehicles that are coming to the intersection. Here is a graphic representation. This is the control situation. So when the minor in a vehicle, an older driver comes to this intersection approach, then if this is a control situation, any vehicle in the vicinity already establishes communication with the central system, with the central terminal. So we know how much time is needed for this vehicle to come to the intersection, and the system will make a decision. If the situation, the time gap is large enough, then we will do nothing, and the driver, depending on the driver's decision making, the driver will start to enter the roads, left turn or right turn. But if the distance is not enough, okay, then the system will issue a warning to the driver inside the vehicle. We have three ways to do it. We can use a flash, and also a flashlight. We can also use a beeping. Okay, we can also use LCD. So we will discuss the results of the testing by using all three different means. So this is the controlled situation. The uncontrolled situation, again, all the vehicles on the main line are not V2I capable. So we'll have to install detectors to measure the approaching speed. Showing here is only one side, but we actually did both sides. Of course, when they do that, it's just for simplicity. Graphically, we only show on one side. So the system will detect the approaching speed of the vehicles, and will communicate with the central terminal. So central terminal will know how many vehicles are approaching and the location of the vehicles when they pass the detector. So the detector cannot be too far away from the intersection, will be in the vicinity for two reasons. One is the communication range. We use Zigbee to communicate the data. Another one is we do not have too much possibilities, too much variations possible, too many variations, or too much a chance for variations in the approaching speed. So we did a field test in this situation by using the detectors to handle these uncontrolled situations. Now here's a video to show the work simulation.
Dr. Yu, the audio is not playing. I'm not sure if that's intentional.
Oh, really? Not playing?
Yeah, you might have to pause your share and then select share audio.
Here. It's a very short one, but okay, maybe we'll have time to come back to that. But there's basically just the system will have a sound to warn, don't turn in situations. And if the system does not give you the warning, then it's your own decision making. The reason we do that is we do not want to bury the liability, okay, issue here. because the system we try to develop, you see here, okay, the system we're trying to develop is a warning system of an unsafe situation. Let's see, no. Anyway, so we have to move ahead. So we try to develop the system that will issue warning if the condition is not safe. Okay, so if the condition is safe, we will not issue any message because of liability concerns. The situation could be if anybody listen to the system and say it's safe to enter and then end up in a crash, then there's a major lawsuit. So what we try to do is to warn them when it's not safe. So hope we understand the concerns we have there. So what you see now is the field equipment. Okay, we have the Zigbee communication. We videotape. We also measure the volume and measure the distance. Remember, we do not want to make it too far so that the vehicles are coming, approaching vehicles will vary speed, and then the system estimation will not be accurate. So here's some data. Look, you see that the screen in detail. We have number of older drivers. We did the different studies at different times. You can see that on the different days. Some of the drivers are not older drivers. You can see that from the top part of the table, the second column and the third column, they highlighted the yellow column. Okay. Well, let me explain how we identify a driver being old or not old. Okay. We are selecting those intersections at the senior citizen, facilities, where we know the people living there, will have to be 65, but there are some age requirements there. And then, but since that road is a public road, it's not just for that senior facility. So we have vehicles coming, from other places to there. So we videotape, and we have places to actually look into the driver very, zoomed up a picture to say whether this is an older driver or not. Okay. Sometimes coming out from the facility also be younger drivers. So for the most part, we believe our data is accurate, but we cannot guarantee 100%. If they say older driver, pretty much is 65 older. But from a younger driver, especially for vehicles coming from not from the facility, definitely we can, say that it's not an older driver. So you can see that. And the lower part of the screen shows different percentages, in terms of the gender and how many turn left, turn right, and so on. And then the next slide will show the results, as you can see here, in uncontrolled situations. Okay, right turn and left turn, we have number of cases. And in the control situations, also for the right turn and left turn, we have different situations. Now, just want you to see people's preference. Okay. Now in here, 18 of the total prefer flashing plus beeping. 2 for the uncontrolled situation, 2 prefer beeping, and 4 prefer LCD. So in here, overwhelmingly, you can see that in the uncontrolled and controlled situations, majority of the people would like to have a flashing plus beeping. So that is not we learn from this and their preference. And you can see the data, this gender distributions, so that we both have a good public insight. I just want to mention this, it's very difficult to conduct the research because this is during the COVID, and the project lasts long because we had to stop the work. Simply, we're not allowed to approach any older people because of the the policy restriction. Anyway, so the last project is based on the previous project on an older driver safety warning system. Now, when we approach the older drivers, and we mentioned about the demand at the level 2, level 3, even technologies. Many of them do not have any idea what it is. Some of them know what technology is, but they're afraid of using it. So in general, okay, even though their vehicles, just some of them, very few of them, have the nice features, but they do not understand. They turn them off. So what we did in this project, this is, by the way, a joint project with the University of Michigan. The other group in Michigan here is to do the training for the students, and we are doing training for the older drivers because of our experience in the previous projects. So the objective is to increase the awareness of the technologies for the older drivers, so that they'll be more, willing to first of all, to understand the technology, and the next step that we need to use to enjoy the benefits, not really or designed for them. Okay, so based on that, we designed a questionnaire, and of course, we accumulated the possible technologies from different places, and we categorize them. You can see the newer features of the vehicles, the level 2 or level 3 technologies are usually on the newer models, of course, and many of them can be switched off and on, and some are just simply provide an alert, and some are physically actually doing the correction. For example, lane tracking, right? It will just physically turn the steering wheel, and so on. But none of the features will actually completely take over. And that's what we emphasize to the older senior people. Don't worry, because they're really afraid of the system taking over. The features you can find from manufacturer's webpage, user's manual, also the AARP workshop. There's a lot of good information there. And we did the work in the Cleveland area. You can see that it's a lot of places that we cover. We did the older driver, older senior community center training for the older people, and then we developed again a questionnaire, and we categorize them into the different features by using the icon, okay, into different categories. In this case, this is a crash avoidance and the mitigation. You can see that all different icons, and then we explain each one of them. Okay, we sit with them, play a video, and give them and charts, and explain them each one what it functions. And for example, this is another one, the braking and the rollover. We put them in one same category to ask them whether they've seen this, if they have seen this, whether they understand, and if they understand it, whether they're willing to use or have used, or if not have not used and they're willing to use it. So we did a training explain. They're not, intimidating. They're just trying to help you, even though you don't understand. It's not something you really should be afraid. It's something that's good for you. It will not drive it for you. It all try to help you. So, and we have a lot of individual, data points, but don't have time to show that. Rather, I'll just collectively show a few slides, and this is data analysis results in terms of the awareness of the new technologies, the autonomous vehicle technologies. And originally, they say this is the yellow bar shows before training. Okay, their awareness is this is unfamiliarity, and then after the training, the familiarity reduced. Okay, you can see that familiarity, the unfamiliarity reduced so much. We have 82, almost 83% reduction. So this obviously shows very effective the training. And this is the one also understanding before the training. Okay, many people, okay, if you look at the number down here, it's like 200, more than 200, show they do not understand. But then after training, you can see we have a 53% of reduction. So, so like half of that say that they understand the technology and so on. Here are just some examples to show the different, different answers that they could provide, and we do the data analysis. And this one shows acceptance. Okay, initially we won't have very small percentage. Okay, and Runberg, you can see that as a 50, says they accept technology, but then after the training, you can see that the increase is 472, 473%, and they are willing to say that I'm willing to try, to test, to enjoy. So this is we can see this is like collectively speaking, the training is very effective. So concluding for this project, a lot of details we will not have time to discuss. You have to do a very good logical planning because you're handling, older drivers. Some older drivers will have, a different special needs, even though they're still driving. And so we'll have to do a very good planning in terms of the scheduling and the location selection. And depending on the feature, the category, up to 27% of the responders are confident with the current driving. So they answer that we do not need anything new. We're fine with what we're doing. I've been doing this for 30, 40 years. I don't need anything. So I mean, or even 50 years, people say that. Okay, we do have drivers as old as like a 90-year-old, and of course, 60 some also we have. So they said that they're very confident with their skills and their experience. They do not need any help. So you can see that this is a big percentage. And you can see most of the responders, however, they feel very positive about this new technology and they're willing to learn and try more. And of course, they are very thankful that I will do this for them. And but then the last part, I see that still there's unknown percentage of the people who do not care about this, training and the technology and the education. And some we heard from, some after listening to us, they don't even show up. So this concludes this presentation. And also it concludes my of the project, also concludes my presentation. I'm sorry, my voice, it's a little cracked because it didn't feel very well recently, but I appreciate everybody's time. And if you have any questions, I'll be happy to answer.
Awesome. Thank you so much, Dr. Yi. Yeah, we have a few questions in the chat, and I know you have to run to another meeting, so we will keep things relatively brief. So our first question is, in your opinion, which U.S. states are farthest along in preparation for implementing CAV technologies?
Very good question. And I want to find out also. Honestly, I don't know, but everybody is doing something. Just like it's very quickly, I don't know, I won't say not every week, but every few, a couple of weeks you hear, new things coming out from different states. But a good question.
Excellent. The next one is, love seeing a funded project on helping older adults with gap selection. Do reach out if you want help with that, as it's squarely in my cognitive aging / transportation technology wheelhouse. What do you believe should be the primary modality used by the proposed system in communicating when, where safe gaps open up? Assuming you are testing the design, how do you propose testing this in a simulator without causing high levels of simulation sickness in your older driver participants?
Yeah, we're trying to, first of all, we did a simulation. I didn't have time to do the presentation to explain the details. We did a simulation and we built a vSIM-based model and to simulate the situation, and they found, very useful. So in a field test there, we did the actual case involving the drivers. Again, it's very difficult to get the drivers during those, difficult times. And when it's all open and we can approach older drivers, we managed to do this test. Now, possibly, I say possibly if we can invite older driver to a human factor lab, which we don't have in the University of Akron, to do this kind of test, then they maybe provide some additional information. So the drivers again in the driving simulator, and you see the screen, vehicles coming, you report yourself in the kind of like semi-realistic situation because you're sitting in a vehicle. But we're still thinking in the field, probably it will provide more direct, especially because everything is new. The visual spatial judgment for the drivers, I think, will be better than sitting in the human factor lab. But it's good. I mean, if they can do that, definitely you can get an additional information. I cannot hear you, Kevin. Kevin?
Thank you. Appreciate it. Can the research make a compelling case to convince NHTSA to make ADAS standard like airbags?
I cannot answer that, but we're just trying to provide enough information. For example, the older drivers we approached, I mean, we didn't know that before the study. We didn't know whether the flashing and the beeping and also LCD, which one really is a better choice. See, from the study, we know that most people prefer flashing with beeping, but LCD is ranked the lowest. So that's something we learned, and that information can be forward to the manufacturers and system developers.
Excellent, thank you. One person recommends warm water and honey and a little lemon juice with your throat. So something worth trying.
Thank you very much.
We'll do one more here before we wrap things up. Dr. Yi, are you aware of this work on fuel economy impacts of platooning? I'll throw the note in here so you can look at it. Basically, this is for Class 8 internal combustion engine vehicles, but it shows diminishing returns for closer following distances due to the need for engine fan having to run more frequently. Let me throw that in the chat, and maybe you can give us your thoughts.
Yeah, if you look at the literature, there's one, I see quite a few, putting out that the platooning can save gas. Okay, so but for our study, we have not factored that into consideration when we did our the impact study of the environmental conditions on the autonomous vehicle fleet operation, simply because we put safety as the major criteria. But we can discuss on that. But I've read platooning's advantage, especially trucks. Trucks platooning, people mention that there's a lot of advantages in terms of the energy saving.
Well, thank you for your time, Dr. Yi. I just want to wrap things up here just briefly. So obviously we want to thank Dr. Yi for taking time out of his busy schedule to join us today. If you're interested in learning more about these projects that his team has led for the Center for Connected and Automated Transportation, the link is in the chat box. If you missed any part of today's presentation, it will be uploaded to the CCAT YouTube channel on Tuesday, February 27th. So if you're not subscribed, the link is in the chat box. Make sure you turn on notifications to get notified when the video is released. Before we close out, I just wanted to let everyone know that we have our next upcoming event is our distinguished lecture with Dr. Carl Wunderlich, who is the director of the Surface Transportation Division at Nobless. He'll be joining us in Ann Arbor and online on Thursday, March 14th. And you can register for that event by clicking the link in the chat box. Finally, one more thing, I wanted to announce that the CCAT 2024 Global Symposium on Mobility Innovation presented by M-City and Umtree is scheduled for May 21st and 22nd, and it'll be taking place at Washtenaw Community College as well as online. This two-track conference features the latest in transportation issues, including AV safety testing, accessibility, and more. We've just announced our first set of speakers, which include Professor Yiheng Feng from Purdue University, Professor Zila Morley Mao from the University of Michigan, as well as Professor Zhili Zhang from the University of Minnesota. Registration is live, and the early bird rate is still available, so make sure you secure your space now. All right, thank you all. Take care and have a great weekend.